Hello everyone! We are starting our free open lecture in our Discord. If you are a viewer and want to ask questions online and get answers, then join our lectures. You can find the link to Discord in our Telegram channel. And today we are starting our series of lectures on basic algorithms, from simple to complex. Searches, sorts, data structures, various implementations on graphs, trees, heaps, and so on and so forth. There will be many interesting topics, but I won't spoil everything. And today our first lecture is on binary search. This is one of the simplest algorithms, and here is its definition. Binary search, also known as binary search, is an algorithm for finding an element in a sorted array, or, for example, some kind of vector. This is, and more for practice because these algorithms are mainly used in competitions in various scenarios, using the division of the array in half. Accordingly, the properties for this array, properties or rules rather, are that it should be an array, a sequence, or some function, meaning something sequential, and it should be sorted in ascending order. For example, if we have an array 1, 2, 3, 4, 5, we can apply binary search to it. Everything is sequential, and we understand where to move. If the array is unordered, like -1, 3, -2, 8, 12, then 3 again, we won't understand what to do, what I was talking about, what it means to move, and so on and so forth. So the purpose, it is used in computer science, computational mathematics, and mathematical programming. That is, these are general purposes, more like overall definitions. So, an example of the work. This is an example of the work, which has a very good picture. I'll show it to you now. Here it is. This is an example of how it works. It segments parts of the array in this manner. And accordingly, now we will examine this in detail as an example. And so, accordingly, he says, a comparison of binary search with linear search when we proceed. That is, obviously, this search is much faster. And here it shows the number of steps, which in this case is 2, and then on the third step, on the fourth it finds it, or in this case, on the third. Here it goes through everything, and the number of steps is only 11. Of course, if the element is the last one, then the number of steps will be the length of the array, and we will talk about that now. So we are working with an example. If we consider an array, there is a step-by-step algorithm for it. I wrote down a simple array with all elements from 1 to 10. The length of this array is exactly 10. If we look at the indexing of the array, the first element will have an index of 0, then 1, 2, 3, 4, 5, 6, 7, 8, and 9. The last element will have an index of 9. The last index will be the length of the array minus 1, because the indices are shifted by 1 since the numbering starts from 0. So, we have this array, and we make step number 1 by setting a left pointer.
Want to become a great programmer? Subscribe to our Telegram channel.
Again, in an already sorted array, we place the left pointer L at the beginning and the right pointer R at the end, and accordingly, we calculate the average value. The average value is calculated, that is, here it is written L0, R9, and. Here is the formula to determine the initial element. We have a central element which is equal to L plus R divided by 2. If you write this code in Python, integer division is written like this. If you write it from the perspective of mathematical division, it will be a fraction that is L plus R divided by 2 and rounded down. That is, in C++, for example, such a division will work if these are ints and not some doubles or long doubles or floats, and it will immediately round it down. That is, it immediately performs integer rounding down during division, and accordingly, we can therefore subtract the average value using this formula. That is, if we substitute the value of LR into this formula, we get 0 plus 9 divided by 2. We get 4.5. Accordingly, we find that this is the fourth index. That is, here the center will be located. That is, here it is, index 4, 0, 1, 2, 3, 4. Here it is, the central element, and it is a 5. This is needed to determine what is to the left and what is to the right, and thus we will understand what to compare with. We compare with the center, and accordingly, there are such rules. If the element we are looking for, in this case, we are looking for the value number 3, we understand whether it is greater than this 5 or less than this 5, or maybe equal, then in this case we can understand. If it is less than 5, then it is located in the left segment, that is in this one. If it is greater, then it is located in the right segment, and thus we have a section. And if we find it immediately, That is, if the central element is equal to our value, then in this case we immediately output the answer. That is, we immediately return the index of the central element at this step. And then again, what happens? To take the left segment, for example, our number is 3, and there would also be the number 8. For the number 3, we shift the right boundary to this 4. That is, we will work only within the context of this segment. We will shift it to the 4. If we had some element number 8, then we would have to move this left index to this 6 and work with this segment. Thus, we can quickly cut off half of the array we have taken. So, in this case, here's the whole array. We took a piece of it, some half, and then we will continue the steps and keep cutting it in half. I hope everything is clear here. Next, we recalculate r, setting it to -1, because the value we need is less than the center. Accordingly, we move this right boundary here in the future, and accordingly we get that r equals 3, and continue to perform this step until we find the element we need, or stop when the left and right indices point to the same element. Well, because such an element might not exist, so here's what happens next. We have the left and we have the right element. This shift to 4 has already occurred, specifically to the value 4, which is the third index. And here, I'm kind of summarizing that we have L equals sign 0 and R equals sign 3. Similarly, using the same formula, we calculate the middle, which is the center, and we get that it equals 1. So we set mid, which is at the first index. Here, mid represents indices, not values, so don't confuse them. Accordingly, R with the index of middle equals the target. In this case, we return the center. In this instance, our middle is not at the value we are looking for. The target is the value we want to find, in case it wasn't clear from the summary. So our middle is at 2. So the 2 is not what we want to find, so nothing will be returned here. Accordingly, we will compare. Is the value at the center greater or less? So obviously R3 is greater than 2, greater than this value. Accordingly, R equals mid1 won't really work for us, because the value is not less, but greater. And this condition will be met when we move the left index to mid1, that is, right here, exactly to 3. In the next step, the center will be here. And also, the left element will also be here. So they will be positioned like this, for example. The left element will be on 3, and then the other one will still remain on 4. Therefore, the second index will again be here, and thus, the second index too will also stay right there. We add all this up, and get 5 divided by 2, which equals approximately 2. So our middle point is going to end up being on exactly same element as where we have placed our left, because 5 divided by 2 once more results in a value of around about 2. Therefore, here, we return answer number 2, since centerpiece matches with target value we're searching for. If you have additional steps involved, for instance, if your array isn't just 10 elements but rather extends into millions, such as 9 million, the principle remains unchanged. The array must always stay sorted, while number steps required would simply increase significantly higher than before. Thus, asymptotic complexity could easily calculated both best worst cases scenarios respectively. In optimal scenario, it becomes 1, implying first middle taken during initial step immediately equates desired search term sought after. For instance, if looking specific numeric figure, say 5, and central position happens land directly upon said numeral, we'd instantly return corresponding indexed location without delay. Accordingly, this is from 1, meaning in one operation. In the worst case, this is when the element we need is in the very last segment, which is of length 2. We constantly halve, meaning we have a halving process that can be represented as 2 to the power of n. Therefore, the logarithm base 2 of n, or more precisely, the logarithm of n base 2, represents the complexity of this algorithm. This constant division by 2 allows us to write such a logarithmic formula. If there is no understanding of how the definition works, or what a logarithm is, one can read about the properties of logarithms and how they are formed on the internet. So here this list is divided into 2 parts, and only one of them is taken. That is, we either cut off the right part from the taken one, or the left part from the taken one, and so on, making the cuts. Accordingly, you can trace this a little further by length. Initially we had 9, then it was immediately divided by 4, which was 2, then it was immediately divided again, resulting in 3, 2, and so on. These are the kinds of divisions we will have. Next, the implementation of this code in pseudocode, that is, writing it in pseudocode with comments so that everything is clear to everyone. We have a binary search function, and just like in the condition, we pass it a list and a value. Our left value is 0, and the right value is the length of the array minus 1. This can be written simply as the length of the array in terms of indexing the last element. As long as the left has not converged with the right, meaning it is either less than or until they meet at one element, it does the following. It determines the central element using the same formula with integer division. Then it compares the central element with the number we are looking for. If they match, we return the middle. If the middle is less than what we are looking for, we move the left boundary. If it is greater, we move the right boundary, and so on. If the element is not found at all, in the very last case, we return -1 because such an element does not exist. That is, we can return -1 because the indexing we return after this function starts from 0 and above. That is, an index of -1 does not exist in the array, and when -1 is returned, it is very easy to understand that this index does not exist in the array, meaning that such an element is not in the array. Accordingly, the same codes follow, but the implementation is in Python without comments. Here you can see a very similar code if you read it in another language. And then we have the implementation in C++. This is specifically an Olympiad implementation that can be used without any issues and it will work. And with that, the lecture has come to an end. Thank you all. See you in the next lectures.
Want to become a great programmer? Subscribe to our Telegram channel.